Imagine a human tribe living in the island of Zanzibar, and they look across the water and they see this huge mass of land, which is Africa, and assume that they were the only humans on Earth. And then some of them think, if we kind of build something to cross this water and go and live in that large land that we see, what would it be like? And the answers, of course, if they were to cross the water, they could colonize the whole planet Earth. And now we are in a similar situation with the colonization of space. Moving from Zanzibar to Africa, increase the carrying capacity by maybe, let's say, 1,000 times, 10,000 times, maybe even 1,000,000 times. I don't know. I mean, you can do the math. But the point being that if we were to colonize space, the expansion in carrying capacity would be far larger than moving from Zanzibar to Africa. But then, of course, the question is that true? And if to answer the question, we need to, do some proper engineering calculations about what exactly is the opportunity that exists if humans were to colonize space. Yeah. So in the chapter of my book, there is this section in which I talk about colonizing our solar system. And later I talk about colonizing our galaxy, and then whether it's possible to colonize other galaxies. And these are not, wishful thinking. These are actual numbers which have been the math and the engineering issues are worked out. And the results that are there should be like accurate within maybe a third of an order of magnitude. An order of magnitude is a factor of 10. So I would say that within a third, this way or that way, these numbers should be accurate. So we are going to look at building of space habitations. And these space habitations, when you think of habitations in space, there are there are four major issues that you should consider first. Okay, now the first is gravity. What we know is that human bodies don't develop properly in the absence of Earth-like gravity. There are problems with the immune system and stuff like that. So we need the proper amount of gravity. Then we need agriculture, because if we are going to really say that we are going to go and live in space, then obviously if we are to have to send food from Earth to space, that's not really an expansion of humanity. A true expansion of humanity would be when space is actually able to provide everything that we need for life. So that means that we have to develop agriculture. Now, space, as we now know, there is a challenge of radiation, and we need protection from radiation. And finally, the claim is that there are a lot of resources in space. If that is the claim, that we should really go to space because there's so much more resources, physical resources in space, then space should be able to provide us luxurious living. And really, I mean, if you're going to make all that effort of getting to space, you don't want to live in like you want to have a great life. Okay, so it has to have luxurious accommodation. So these are the 4 requirements for colonizing space. And to fulfill these requirements, I have in this book chapter the design of a space habitation. And you can see that this space habitation that the cross-sectional view of it, it shows that it has agriculture zones, it has lakes, it has parks, condos, offices, malls, factories, stadiums, hiking trails, bike paths. So this is what we as modern humans consider to be the necessities for a good life. It has everything. So this space habitation, this design, which I go into detail in the book, has all these, meets all these requirements. And there is one very important number which comes out of the design of this space habitation. And that number, what is that number? That number is the amount of mass needed per capita to build these habitations. If the amount of resources in space was enough for, let's say, 1 million humans, we are already about 8 billion on Earth. And then you make that effort and you say, oh yeah, we can go to space and we can have a really great life there. And so the question is, for how many people? And the answer depends upon how much mass is needed and how much mass is available in space. So that is a very important number. And throughout this book, that number will appear again and again and again. And that number for this space habitation is 1.42 trillion kilograms for a space habitation which houses 50,000 humans in luxury, living lives of luxury. And that 1.42 trillion translates to something like the carrying capacity of space of let's say, just our solar system, not being 1 million. That was just a number I kind of put out there to make a point. Okay. So the carrying capacity of our solar system, remember the carrying capacity of Earth is maybe 8 billion. That's where we are right now. I can't really see the population of Earth increasing significantly beyond what it already is. So the carrying capacity of our solar system, based on the amount of mass that is needed to build these space habitations, is 50,000 trillion. Yes, you heard that right. 50,000 trillion humans can be provided lives of luxury by colonizing our solar system. know the details of this, the design of this space habitation, you should get the book. So when I made the previous video, I thought that I'll actually stop at that point, but then I decided, let me give you a few more details about the space habitation where someday in the future, most of humanity is going to live. And, even though the space habitation design, which is in my book, is my design, and this was mainly, I thought of it like I would lie at night trying to fall asleep. And this was before I started listening to audiobooks. And then I would just like try to think of something to fall asleep. And then I would think of the space habitation and how one could build that habitation. Now, of course, later I came across space habitations which, two people are especially notable for having pioneered the idea. They are Bernal and Neil, Gerard O'Neill. So let's take a look at them. This is Gerard O'Neill. He was a professor of physics, and this is Bernal. So acknowledgements to these visionaries who pioneered these ideas. Okay. So getting back to my design, this was the habitation. These are, what you see over here are these concentric circles with various layers. And the most important layer to start with is, of course, the other agricultural layers, followed by the habitation layers. So in the middle of it, it's all air. And then you have this, the tube, which is the innermost tube, is where the humans will live. And then you have successive agricultural layers. There'll be actually 5 agricultural layers. So based on the calculations, which I'll provide, some of the calculations, not all. For all the calculations, you need the book. For some of the the calculations will say that the mass of this habitation, which has a population of 50,000, the mass is going to be 1.42 trillion kilograms. The diameter, I've just set it as a mile. So you're living here, and then you're looking up, and your, what do you call that, upstairs neighbor, that's the person living at the other end of the tube. So what I mean to say is that suppose you're like living over here, and then there's somebody living there. So you look up and you see their house a mile away from you. You should not feel claustrophobic. It's like being in this gigantic mall with a 1 mile high ceiling. That's what it'll be like. And it'll be all very green and pretty, and there'll be water bodies, there'll be parks, there'll be flower beds, there'll be beaches. It's just going to be fantastic. And it's going to be about 11.3 kilometers long. And where does actually that number, what is the major determinant of that number, 11.3 kilometers? It's essentially the amount of agricultural land that you'll need to provide sufficient food for the population of 50,000. And I'll come back to that later. And that agricultural land will be, you need some like topsoil, and lunar regolith is a nice candidate. The moon is not too far away, can be easily mined using electromagnetic railguns. And You can also grow food in water, and NASA has done some experiments about it. Okay, so let's get to like the details of the needed agricultural land. And Earth's population is currently 7.85 billion. So the agricultural area per human is about 5,670 meters square. You have to get the estimate of how much of the land on Earth is used for agriculture. So based on that, we get to 5,670 meters square. And if with that as the per capita requirement, we come up that the required agricultural area in the space habitation will be 284 million meters square. And we assume that the topsoil depth of 1.5 meters will be enough to provide the growing surface needed for crops and other food. Okay, now remember there are these 5 of these layers, right? And the question is, these layers actually they solve 2 problems, 2 very important problems. One is, they produce food, and the second is that they protect the inhabitants who live in the inner tube from radiation. Radiation is a huge problem in space. And you think of like going and living on Mars. Unfortunately, you'll have to live under a very thick roof if you want to live on another planet, unless it has the features of Earth, which is the atmosphere and the magnetosphere, which protect us from radiation. So, how much shielding do we need? Well, according to NASA, we need about 11,000 kilograms per meter square of shielding. And this is from a book by Marotta and Clovis. It's a very good book. So we have now stacked 5 agricultural layers, each of depth 1.5 meters. And so how much shielding does it produce? Well, these 5 layers will produce a shielding of 12,000 kilograms per meter square, which exceeds NASA's requirements. So these agricultural layers will provide sufficient shielding. So now we have land for agriculture. So what is the other thing we need for agriculture? We need energy, or free energy, as it is called. And this energy is going to be used for grow lights, which will provide the energy necessary for photosynthesis by the plants. And we have an estimate. We can make an estimate of how much energy will be needed, because grow lights are commercially popular. So I took some numbers that I found from some commercial vendors. And the final number I came up with is that for these 284 million meters square of agricultural land, the amount of energy that will be needed will be 15.98 gigawatts. So, energy is needed for agriculture. That's the main need for energy. That's also needed for other things like light, or if you have some transport and stuff like that. So I'm just going to assume that the energy needed for other purposes is what the average US citizen consumes currently, which is about 3.7 kilowatt. And then you multiply that by 50,000 inhabitants in the space habitation, and you end up with the total number, the total amount of energy to be 16.2 gigawatts. Now, the solar panels I had calculated earlier, the solar panels are going to provide about 24.7 gigawatts, but we are going to assume that, well, that's the energy incident on the solar panels, which is about 1368 watts per meter square on Earth orbit. So not like on the surface of Earth, because a lot of that energy is lost when it travels through the atmosphere, when the sunlight travels through the atmosphere. So this is at the Earth orbit without any interference by any atmosphere. So that is about 24.7 gigawatts, but we can't assume 100% efficiency for the solar panels. So we're just going to assume, like, let's say 50% efficiency. So with 50% efficiency, the solar panels are going to provide us with 12.35 gigawatts of energy for the space habitation, which is less than what we have calculated. Our need was about 16.2. Now, there are a couple of things you can do to make up this shortfall. One is that a lot of the energy which is used for agriculture can again be recovered as biofuels. Or you can simply extend the solar panels, like wings outside the space habitation. So the bottom line is that energy is not a problem. You have plentiful energy in space.